Welcome to today's presentation entitled Introduction to Digital Signal Processing. My name is Dr. Jim Batty, and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center Flight Mechanics Technical Discipline Team. This presentation is part 2 of a 4-part discussion about digital signal processing and is sponsored by the NESC as part of an educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. Today's presentation is entitled Power Spectral Density Basics. This slide presents an overview of what was presented in Part 1 of this discussion, what will be presented in Part 2, today's discussion, as well as in Parts 3 and 4. In the previous discussion, entitled Mathematical Concepts, we defined the definitions, mathematical prerequisites, and application techniques that are used for digital signal processing, including Fourier transforms and convolution, discrete Fourier transforms, and fast Fourier transform, which is an algorithm for efficiently computing discrete Fourier transforms. We also discussed the Shannon Sampling Theorem and data aliasing, which is related to the frequency at which you sample a time signal and how that's important in capturing the true characteristics of the signal. In today's discussion, Part 2, which is entitled Power Spectral Density Basics, we will cover power spectral density and how it's used to estimate the spectral characteristics of waveforms, including a PSD demonstration where we show an example of a computed waveform that consists of several different sinusoids, a constant bias term, and a random component, and illustrate how the PSD can be used to identify each of these characteristics within that waveform. In Part 3, which is entitled Implementing Discrete Filters, we'll start off by showing how to convert from continuous Laplace domain filters to discrete Z-domain filters using a technique referred to as Tustin's rule, or also the bilinear transformation. We'll also summarize how each of those the continuous Laplace domain filters can be implemented in a time domain simulation as well as their counterparts in the discrete domain. We'll also show how to implement recursive filters to implement those discrete filters. In Part 4 of this presentation, which is entitled Typical GNC Applications, we'll discuss how you actually use the concepts that were developed in the first 3 parts of the discussion to perform tasks that are typically done in a GNC situation. We'll discuss things such as normalized frequency, what it means and what it really corresponds to, the methods that you could use to verify the transfer function magnitude and phase of a discrete filter once you've been given the coefficients. And you can use that technique to verify those discrete coefficients actually do give you the filter characteristics you're looking for. We'll also show an example of how you would use the discrete filter to implement a notch low-pass filter that we will use to factor or to filter a input waveform that has higher frequency signals that will be attenuated both within the notch and at higher frequencies as well. Power spectral density, also known as PSD, is a technique for estimating the spectral or frequency content of signal waveforms. PSDs use FFTs, or fast Fourier transforms, to efficiently compute the discrete Fourier transforms of the input signal that are then used to extract its frequency content. But it's important distinction to note that PSDs and FFTs really are not different things. People sometimes confuse those and wonder, well, I can use a FFT to compute a PSD as well, can't I? And the answer is yes, and actually most PSD packages or analysis tools actually use fast Fourier transforms to compute the discrete Fourier transforms. That's just a more efficient way of computing it compared to the more direct methods that you would find in the mathematics. And this was discussed at length in the first presentation, Part 1 of this presentation. The PSD is a useful tool for evaluating the periodic content of signals from some device, a piece of hardware, for instance sensors, that you could use to characterize the output of that sensor for modeling purposes in perhaps a simulation, or for requirements compliance, such as if you have a specification that it has to meet, you can actually take laboratory data that was collected for the device, compute a PSD of it, and evaluate where it has various signal characteristics frequency-wise. The PSD represents, per its name, power spectral density. It's the density of the signal squared magnitude at a particular frequency. And it's typically presented as a plot or a graph of PSD units square per hertz at versus frequency. And a couple of things are noteworthy about that. The integral of the signal's PSD provides the signal's mean square value. And you can imagine if you integrate a signal that's power or unit square per hertz over some frequency range, you will get out the total power or unit squared. And then the square root of that then would provide the signal mean square value. Non-zero mean signals are usually detrended before you compute the PSD. And what detrended means in this sense is you remove the mean value. If it's got a constant trend, meaning a constant bias, you would typically remove that before you compute the PSD. And you can also, another detrending technique that's used in PSD packages is you might have a linear bias, a bias that continues as a function of time. And so those can also be removed. And we'll discuss that a little bit more as to the detrend options, as they might be called, in some of the analysis tools for computing PSDs, as you might find in a package such as MATLAB or Octave. The DFT size and the sampling is very important with the overall outcome that you're going to get when you compute a PSD of a signal. So it warrants a little bit of a discussion here. The DFT size that's used to compute them, the PSDs, actually affects the resolution of the calculation of the spectral content. The larger the DFT size you have, the greater the resolution of those calculations. However, there's a downside to that if you're not prepared for it. The higher resolution can introduce some unexpected results that you might find interesting, and we'll have some examples in a few charts that will elaborate a little bit more on that. The placement of the spectral content in the sample data with respect to what's referred to as discrete Fourier transform basis frequencies can also affect the output DFT calculation and can provide some unexpected results, again, if you're not prepared for that. There's a technique used in PSD referred to as windows that can be used to eliminate some of these issues, and we'll show some examples of how windows can remove some of these unexpected results, as well as the different options one might have for different kinds of windows that are available with PSD packages that are available. Basis frequencies of a DFT refers to the specific sinusoids used in the calculation of the discrete Fourier transform coefficients that then can be used to extract the spectral content of the sequence being analyzed. Those same basis frequencies, by the way, are also used in what's referred to as a synthesis equation if you want to take discrete Fourier transform coefficients and recreate the time sequence that created them in the first place. Those basis frequencies are normalized to the sample frequency, and they run for a real discrete Fourier transform from 0 to 0.5 normalized frequency. That means from 0 to 0.5 of the sample frequency, and that half the sample frequency is referred to as the Nyquist frequency, which we discussed in part 1 of this discussion, primarily with respect to the discussion of Shannon Sampling Theorem. The basis frequency of an n-sample DFT occur at integer multiples of 1 over n. Since the sine and cosine functions used to create or compute the DFT coefficients use 2 pi k over n as the frequencies of those sinusoids, where k varies from 0, 1, 2, 3, up to n over 2, where n is the number of samples in the sequence you're analyzing. Shown below here is the calculation of the real and imaginary parts of the DFT. As you see, the real is a summation from m equals 0 to n minus 1 of x sub m, which means the individual samples of the time signal, multiplied by cosine 2 pi k over n times m. The imaginary part is a summation from m equals 0 to n minus 1 of x sub m sine of 2 pi k over n times m, where in both of these the k index in the coefficients, it generates n over 2 plus 1 coefficients. The k runs from 0, 1, 2 up to n divided by 2. For example, a 256-point DFT would have basis frequencies that are multiples of 1 over 256. So basically, they would have a normalized frequency range of integer multiples of 0.003906. And if the sample sequence x of n contains frequencies at frequencies that are not aligned with one of these basis frequencies, the spectral energy at that frequency will be spread among adjacent basis frequencies. And that'll cause some kind of mixing of the frequency content that will have to be sorted out. And then some of the techniques that we'll talk about farther on in this discussion will help minimize some of those results of sharing the signal energy among adjacent sinusoids and trying to sort out where the frequency really occurs. As an example of FFT size, consider a 256-point sample of the sequence from a single sinusoid, where the sequence is defined as the n samples of this signal are sine of 2 pi f times the 0, 1, 2, 3, up to 255, where in this example I'm going to pick f very specifically to be 0.19922, and that was selected to match one of the basis frequencies of that 256-point DFT, which happens to be 51 over 256. So with this single basis frequency in the spectrum of the sequence x of n, the DFT should produce a single spike at a normalized frequency of 0.19922. And so first, in this example, we'll compute a 256-point DFT and demonstrate the alignment of the basis frequencies at that normalized frequency, which means that 256-point DFT will have one non-zero output, and that frequency of the non-zero point will occur at 0.19922. All other points in the 256-point DFT will have a value of 0. Then we'll compute the DFTs of that same sequence with larger size DFTs. We'll do a 512-point and a 4096-point and compare the magnitude versus frequency with that 256-point DFT to illustrate the importance of FFT size. So first we'll look at the DFT computed from the 256-point DFT of that 256-point sample, where again the frequency of the input waveform was selected to be at one of the basis frequencies that occurs at 0.19922. And as you see, plotted in the figure on the left is the DFT output and its magnitude versus normalized frequency, where it's shown with a red line with a circle for the individual plotting symbols so that you can see where they're 0 and where they're non-zero. You'll notice a couple of things with that figure. The range of the frequencies is 0 to 0.5, and if you actually looked at the frequency array that we returned from the PSD function for that particular example, the maximum frequency is 0.5, and again that's because a real DFT generates frequencies in the range of 0 to 0.5, where 0.5 represents the Nyquist frequency, or half the sample frequency. And again, those frequencies are normalized to the sample frequency. So again, 0.5 would represent half of the sample frequency. Note again, there's only one point in there where we have a non-zero DFT magnitude, and that occurs what looks real like 0.2, but we'll expand that out a little bit on the slide to the right. And also we'll note the amplitude of that signal is 128. And you might recall from part 1 of this presentation that the discrete Fourier transform coefficients are scaled by n or n over 2 for the end points of the frequency of the discrete Fourier transform. That is at a normalized frequency of 0 and a normalized frequency of 0.5, which occurs for k equals 0 and k equals n over 2 in the summation that we saw a couple of charts earlier. The scaling is the value of n, where n is the number of points. For all other points in between the endpoints, the scaling is n over 2. And in this example, the n for this particular discrete Fourier transform was 256. So the 256 over 2 is 128, and that's what you see as the magnitude of the input signal. Now, again, if we expand around that area of where the non-zero DFT occurs, you'll actually see the blue line that's dotted on the chart to the right actually shows where the peak of that PSD occurs, and where you get the single non-zero point with a value of 128. And you'll see that it does indeed occur at a frequency of 0.19922, and then on either side of that, which is 1 over 256 of a normalized frequency on either side, you see it is actually back to 0 magnitude. So you only have one data point, non-zero, and that occurs right at the normalized frequency that we put in of 0.19922. So now we'll look at larger magnitude sizes of DFTs for that same input signal. We'll keep the same waveform, 256 points, with a input frequency, normalized frequency of 0.19922. Now you'll see when we run larger DFT sizes, 1024 or 4096 points, we start to pick up side lobes, as you see in the figure to the right. Well, what causes those side lobes when we have larger DFTs, and why didn't we see them in this 256 point DFT? The reason is that X sub n that we're looking at, the 256 points of the original sample, is basically a 256 point sample of an infinitely long sinusoidal sequence. Sampling of that infinitely long sequence into a finite sequence of 256 points is equivalent to the convolution of that input sinusoid with a rectangular waveform, or a rectangular window if you want to call it that, that has a value of 1 for k equals 0 to 255 and 0 for k greater than 255. So basically you've put a block window in there and just extracted 256 points and ignored all the rest. What you can see from that is the discrete Fourier transform of a rectangular pulse results in a sinc function. And that can be shown from just the material that was presented in part 1, and you pass a rectangular pulse through it, you'll get a sinc function out, which looks in the time domain like sine x over x or sine t over t if x represents time. And then a rectangular pulse in the time domain would transform via Fourier transforms into a sinc function in the frequency domain. Conversely, a sinc function in the time domain, if you started out with a sinc function and did a Fourier transform of it, it would transform to a rectangular function in the frequency domain. And so the DFT of the samples of that infinitely long sequence is actually the product of the DFT of a sinc function and a DFT of the sinusoidal sequence. And what that results in is basically a sinc function that's centered about the input frequency of that sinusoid. And that's exactly what you see over on the right for the blue line and the darker brown line, which now you start to see what looks kind of like a sinc function that's centered around 0.19922. So the question is also, why don't you see this side lobes in the 256 point DFT? You may recall, if you look carefully at the red line here, that's what was presented a couple of charts ago. Basically, you just get all zeros except at that one peak. The answer is the 256 point DFT lacks the resolution necessary to display them. What it actually shows you is the data where the sinc function crosses back through 0. And you can see that very carefully if you look again at the figure on the right, where this time I've shown just the 256 point DFT and the 512 point. I excluded the higher resolution one. And what you'll see is the 512 points has one additional point that the 256 point doesn't. Each of them goes through the same points where the 256 point DFT had a value of 0 other than at the peak. And the 512 point has an additional point in between those two where it's non-zero as well. And if you looked at the 4096 point DFT on the previous slide, it shows what looks more like a continuous curve between those adjacent points. So it basically, the 256 point DFT is computing the right data, it's just doesn't have high enough resolution to show all the data that's there. Now in the example just presented, that a specific frequency was carefully chosen to align exactly with one of the basis frequencies of the DFT, which, as I said earlier, occurs in a 256 point DFT at integer multiples of 1 over 256. Well, what if the input sequence was not so carefully contrived? And in the real world, that's likely to be the case. It's going to be not necessarily at one of the particular DFT basis frequencies. So again, to illustrate what happens here, we'll take a second example. This time we'll do just what we did before, but in the construction of the 256 point sequence that we're going to compute the for which we'll compute the discrete Fourier transform, we'll change that normalized frequency from 0.19922, which aligned perfectly with one of the basis frequencies, to just 0.2. So again, the equation that you might use in MATLAB or Octave to compute it is shown below. It's x sub n equals sine of 2 pi times 0.2 normalized frequency for the samples 0 to 255, which results in a 256 point sample x sub n. If we compute the discrete Fourier transform of that and then plot out the magnitude of the DFT versus normalized frequency, you'll get the red line is the 256 point DFT of that new sequence. The blue line is a larger resolution or higher resolution 4096 point DFT. Now notice that the 256 point DFT is not a single non-zero spike. The red line shown on the figure on the right, you can actually see again the plotting symbols, the O's or circles are actual data points, and now they are non-zero values at places other than just the single sinusoid that was put in. Well, what causes, well, also and also has some tails around the side where it's not a distinct rise up to that peak. What causes those tails? They're caused by what's referred to as spectral leakage, and what that refers to is what I described earlier. The signal strength of that sinusoid, since it doesn't line up with a particular one single basis frequency, its energy is shared by multiple basis frequencies. However, and that can be kind of somewhat disconcerting, because if you're trying to find a specific frequency at which there's content in a signal, that can be kind of confusing very quickly when if you have multiple frequencies and then all of these get overlapped. So you'd like to find some way to concentrate the energy, even though it's not lined up with a basis frequency. You'd like to concentrate it into a single spike, if you will, in the output that can be useful. And one of the things that can be used to help eliminate those are what I referred to earlier as windows. It's a technique used in the calculation of PSDs. For example, one common example of a filter is a Hamming window, and that's a very specific function as shown in the equation here, where I'll calculate the elements of the window W sub k, which run with indices from 0 to some length m minus 1, and its function is 0.54 minus 0.46 cosine 2 pi k over m minus 1, where again the range of the indices is 0 to m minus 1, where m is just the size of the window. So for this example, using the same input sequence we used for the previous slide, we'll define a 256 point Hamming window, and shown is the equation you used with Octave or MATLAB or some package like that to create the actual window. Then you compute the 256 point DFT of the term-by-term multiplication of x sub n and w sub n. Now this is not convolution, this is just literally multiply term by term the window by the samples that you're processing, x sub n. And then you take the DFT of that result. So shown at the right is the 256 point DFT of for x sub n alone, which is the red line which we showed earlier, and the DFT of the sample x sub n that's been windowed by multiplying it by this 256 point Hamming window. And now you'll notice the tails around the 0.2 frequency are removed. You get nice little clean little pulses, not a single pulse anymore that jumps up at 0.2, but it's most of the tail has been removed, and now it's a more cleaner representation of that single frequency content of 0.2 normalized frequency that we built into the example sequence. You also notice, if you look carefully at the previous slide, the Hamming window removed the tails in the DFT, but they did reduce the peak amplitude a little bit. And that can be a little disconcerting if you're attempting to use the magnitude of the DFT to try to estimate what the actual mean square value of the time sequence that you're evaluating. So you can correct this scaling, if you want to call it, that was introduced by the windowing by normalizing the window before you use it. And that's not absolutely necessary if your intent is just to try to find where the content has frequency, or where the signal has frequency content. And because if you have if you're trying to compute the RMS, obviously you can just compute that directly. You don't need the PSD to compute the RMS for you. But if you want to try to preserve some of the magnitude of the discrete Fourier transform output, you can normalize the window as shown here. Basically, you just divide each of the window samples by the sum of all samples divided by the number of samples. And that would be simply the ith value of the window would be the ith window divided by the norm, where the norm is just the sum of all the window coefficients divided by its length. So in this case, what we had before of a 256-point window, we just sum up the value of all the window coefficients divided by 256. That would be the norm. Then you go back and divide each of the elements of the window by norm. If you do that then, and recompute the DFT of the sequence using that normalized Hamming window, you get the green line that is shown in the figure to the right. And now you'll notice, again, we've removed the tails that you see from the red curve, which was the DFT without any windowing. And now we still have a nice, sharp, distinct pulse that the windowing produced, but now the magnitude of the discrete Fourier transform is back to where it was originally. And as I mentioned earlier, many analysis packages such as MATLAB and Octave provide built-in PSD functions, but if you actually attempt to use those or try to get some help using the help function on them, you'll get, if you're not familiar with PSDs, you'll get a lot of very unfamiliar concepts that are being provided in that help. As I said, you'll get lots of examples of how to use different windowing methods, which we covered briefly, so you're not totally unfamiliar with them, but there's many different kinds of windows. There's Hamming windows, which we described earlier. There's Hanning windows. There's Blackman windows. There's rectangular windows. There's triangular windows. There's all sorts of other windows. There's, as I described earlier, normalized frequencies. Again, you've been introduced a little bit to normalized frequencies, so you may not be totally in the dark here. But again, if you don't provide the sample frequency that the data was taken at, it'll just return everything in a frequency range of usually 0 to 0.5. So then that's also a source of confusion. When people get the PSD back, they don't know quite how to interpret what those frequencies of 0 to 0.5 means. Also, those PSD functions have other obscure sounding things like overlapping and detrending. We'll discuss those a little bit in the next few slides as well. Also use something called periodograms, which you wonder, what is a periodogram? And basically all that is just it's basically the name that was given traditionally for computing spectral content of data. Periodic grams, I guess is what that refers to, and it's a visualization of the spectral content. And then also how to scale the outputs to something meaningful. So if you get a PSD out and it comes out in units squared per hertz or units squared per whatever, how do you convert that back into something that's like volts or degrees per second or whatever the signal might be that you're processing? As I mentioned before, if you're using MATLAB or Octave, at the command prompt you can type help PSD and you'll get some definition of how to use some of the arguments inside the PSD function. As I mentioned earlier, we'll have a demonstration for that coming up. So to do the demonstration, what we'll do is create a 512.0.2 normalized frequency sinusoid. And again, this 0.2 normalized frequency will not line up directly with a 512-point DFT. As you recall, the frequency would need to be 0.19922 to line up with a single basis frequency, but we basically have already covered why that's important and what you get out. So again, we'll create 512 points with a normalized frequency of 0.2, and we'll call the PSD function. Here's an example shown here, how you'd call it with no optional arguments. And most of these packages, like MATLAB and Octave, if you just call the PSD function, as shown here, just PSD parenthesis x, in general it'll create a plot of the PSD. Although if you want to capture the outputs, you can actually load them into arrays. So as the second example shows, you just load pxx and frequency equals PSD. So then that will return the PSD itself in the variable I call pxx, and it will return the frequencies into the array called FREQ. And then you can plot that out manually or have it plotted automatically. And what you'll notice again, what you'll get out if you let it auto-scale is the frequency range will be 0 to 0.5. So the only data points will be between 0 and 0.5 normalized frequency. Again, the 0.5 refers to 1/2 the sample frequency, or otherwise known as the Nyquist frequency. Now if you want to rescale that previous example again, as I described, around the 0.2 range where we put in the single discrete frequency, you'll get the red line that you see in this figure to the right. You notice it's not quite symmetric. It's got some, asymmetries around the 0.2, and that's caused by the spectral leakage that we referred to before. That there, number two are two things going on. Number one is the input frequency is not at one of the basis frequencies of the PSD, and so we'll repeat this example with the 0.2 changed to 0.19922, which again is one of the basis frequencies of a 512-point DFT. It happens to equal 102 over 512 is what 19922 corresponds to. So then if we put in 0.19922 and recompute the PSD, you'll see now we get the blue line, which is now nice and symmetric around 0.19922. And so the asymmetry that you saw in the red line is caused by the spectral leakage of the PSD being contributing to several several basis frequencies at a range around 0.19922. And again, with most of these techniques, you can then just directly, once you have the PSD array, you can compute the area under the PSD curve, if you will, which ought to equal to the square root of it, ought to equal the RMS value of the input signal. And as an example to show you how you can double check what you have out, if the actual RMS value for the input sinusoid of sine 2 pi to 0.2 should be 1 over square root of 2, or 0.707. If you actually sum up the PXX array times the frequency per sample that's in that PSD, as shown by the little example calculation in MATLAB there, you would see that the actual value that it came out with was 0.7071, etc. So it's very close to the actual RMS value. And again, we'll talk about normalized frequency versus sample frequency. And in most of these application packages, if you don't provide, one of the optional inputs for it is the frequency at which the data was sampled. If you provide that, it will actually scale the normalized frequency back to so it comes out in hertz, for instance, or radians per second, or whatever the frequency was. If you don't provide it, again, it assumes the sample frequency is 1, so what comes out again, as we described, is just 0 to 0.5, or 0 to half of the default sample frequency of 1 hertz. However, one thing I'll note, and we'll show this in an example here, was that's for real sequences, x of n. It turns out if you were to provide the PSD function a complex sequence, you would get out frequencies in the range of 0 to 1. And we'll show an example of that coming up here in just a moment. But again, if you provide the sample frequency, the frequency array that gets returned has units of hertz as opposed to normalized frequency. So for example, if you look at the code, the sample MATLAB command at the bottom of this slide, where we call the PSD function and we provide it the first argument, which is a sequence of values x. The second argument, I'll let it default. I'll put a null input, and that just happens to be the size of the PSD you want it to compute. If you don't provide a size, it will just make the size of the PSD the same as the size of the input sequence. In this case, it will be 512-point DFTs used to compute that PSD. The third argument is a sample frequency. In this case, I'll just say it happened to correspond to a 1,000 hertz sample of a signal. Now when you plot out the PSD versus frequency, you'll notice it's actually in hertz. It's no longer normalized frequency, and now you can see the peak there at 199.22 hertz, which is what that normalized frequency of 0.19922 would be for a 1,000 hertz samples. And note the magnitude of the PSD is 1,000th of what it was before. Remember before it was up around 170, now it's around 0.17. What that is before, the units of that PSD when it was normalized frequency as the frequency range was really units squared per sample, not units squared per hertz. So when you convert it to actual units squared per hertz, it divides the PSD from a normalized frequency range and divides it by the frequency range to convert it to units squared per hertz, which is typically what you're expecting when you're processing some sort of data. Like if you look at typical specs for sensors and things like that, they'll show like a noise spectrum of PSD per hertz is the amplitude. So that's important to note how providing the frequency to the PSD function does change the amplitude of the output PSD. And here's an example of the size of the DFT, how it affects the shape of the resultant PSD you get out of it. So we'll go back to our example again. This is a 512 point input sequence, so 512 points in it, and with a normalized frequency of 0.2. And this time we will specify to the PSD function that we want it to use 128 point DFTs, 256 point DFTs, or 512 point DFTs. And so shown at the bottom of this slide is the command you would use to create each of these PSD versus frequency outputs. And then we plotted them all out together as shown on the figure on the right. And you'll notice that the size of the DFT affects the peak and the resolution of the PSD, but the frequency content hasn't been altered. In other words, you still see them at the 0.19922 frequency, but and also it does not affect the area under the PSD curve. I didn't show it here, but if you actually took those outputs from those example calls to the PSD function and integrated them as I showed earlier by summing up and dividing by the frequency range of each sample, you get the same PSD of approximately 0.707, which we had showed earlier was the theoretical value that you should get. Again, we talked a little bit about what the units of the PSD. Again, the PSD stands for Power Spectral Density. It's the density of the power in the signal at a function of frequency. So usually it's unit squared per unit frequency. So normally if you've provided the sample frequency, you'll get out the PSD in unit squared per hertz. If you've not provided the frequency to the PSD function, you'll get unit squared per sample. And that's a very important thing to remember so that you can know how to interpret the numbers you get out. So not only does providing the sample frequency provide an output in the frequency array that's been provided out of the PSD function, so there's now real hertz, it also will adjust the PSD amplitude as well. Or conversely, if you don't provide the sample frequency, you need to remember to adjust the amplitude, knowing that it's unit squared per sample rather than unit squared per hertz. Now, as mentioned earlier and promised, what happens if we don't have a real sequence? We have a complex sequence. Well, in the real world, this is a little bit of an academic exercise, but it's important to discuss a couple of concepts here. In the real world, obviously our sequences would not be complex; they'd be real, since we're talking about real sensors and real signals that are in general are real. But for this example, I'll take the previous sequence that we had defined, X, which was a 512 point single component sinusoid, and I'll create a complex sequence by just adding a very small 0.00001 times I, where I is an imaginary number, to one element. So I just create XC and set it equal to X, and then modify the first element by adding a small fraction of I, or the square root of minus 1, to it. Now I'll call the PSD function with all default inputs and capture the output in PXX and frequency, and I'll plot that out. Now notice a couple of things that are interesting. In the figure on the right now, you'll see the normalized frequency goes from 0 to 1. You'll also notice the red line is the original real sequence PSD, and there you saw it was at a normalized frequency of 0.2, and its values, as you may recall, was approximately 170 units squared per sample. Now, when we created a complex sequence and computed the PSD of it, we have one component at 0.2, the blue line. We also have another component in blue at 0.8. And also, the amplitude of each of those is about half of what it was before, around 85 instead of 170. Okay, what interpretation can you make of this? Again, the 0 to 0.5 normalized frequency is just what we talked about before. It's the range from 0 to the Nyquist frequency. The 0.5 to 1 happens to correspond to negative frequencies that have been flipped over. And what I mean by flipped over is the center there where you see the two arrows together. The range 0 to 0.5 terminates at 0.5 normalized frequency. Minus 0.5 normalized frequency occurs at 0.5 and slightly larger values. And then as you go from 0.5 down to 1, you're going negative frequencies, smaller and smaller and smaller and smaller, until you finally get to 0 negative frequency, is at a normalized frequency of 1. So it basically takes the curve and kind of wraps it on itself, if you will, if you're taking the complex DFT and creating a reel from it. You may have heard the term two-sided PSDs versus one-sided PSDs, and that's exactly what this is. If you have a two-sided PSD, which is the blue line, since it's a complex sequence, the energy from that single sinusoid shows up in a 0.2 normalized frequency as well as a negative 0.2 normalized frequency, which again is shown up as 0.8 normalized frequency. And all the power within that waveform is now shared by the positive frequency and the negative frequency. And that's why the amplitude of the PSD now is half of what it was when it was a real sequence. So if you ever hear the term two-sided PSDs versus one-sided, that's what it's referring to. Now, as mentioned earlier, these packages like MATLAB and Octave, their PSD functions have lots of window options you can pick from to apply windows to the data as it's computing the PSD. And you saw how powerful that was in the past as far as trying to isolate the particular spectral content so that you don't get these issues of spectral leakage or the power of the waveform being shared by adjacent sinusoids basis frequencies in the discrete Fourier transform. So what we'll do here is we'll compute a 4096 point PSD of a real sequence x of n with the frequency of 199.22 hertz. Again, that would result in a placing all the energy at one of the basis frequencies of that sequence. And we'll illustrate some of the different window options that are available. So again, I'll just say in words what the ones are, and then we'll kind of go through each one in a little bit more detail. If you provide a negative window size for the window input, that will result in basically an n-point rectangular window. You could also, if you just provide a positive integer for the window size, that results in, by default, a Hanning window of that size. Then you can also provide string inputs for it. For instance, a Hanning 128 would provide a Hanning window of 128 points, or Hamming 128 would provide a Hamming window of 128. Finally, Blackman, again, is another window that can be used, and Blackman 128, all as a string input, would instruct it to use a Blackman window of 128 points in the process of creating that 4096 point PSD. So the four examples here I've computed and returned into PXX1 and frequency 1, PXX2 and frequency 2, the PSD and frequency range of each of those windowing options. So a 128 point rectangular window, 128 point Hanning window, using that as the default, 128 point Hanning window again as just to illustrate the string input, 128 point Hamming window, and 128 point Blackman window. And shown on the right there are just plots of those particular windows, of those PSDs. And again, you see I've provided in the input sequence to each of those PSD functions, I provided also the non-default input for 4096 points. I want the PSDs each to be at 4096 points. I've told it the sample rate was 1000 hertz. So then again, the frequencies that come back are in hertz now, not normalized frequency. And you can see what you get out of it. The various windows, they all do a good job of removing the little side lobes that might appear with the large size PSD that we saw earlier in the example when we did not window it. You may recall the discussion of the sync function, little side lobes that show up around the peak where the data really is. But you can see that all of these do a real good job of smoothing out the PSD. So now, if you had multiple frequencies in this signal that you were looking at, they wouldn't all get muddled together where they would without the windows, so that you wouldn't be able to isolate what's real data and what are these side lobes from the sync function, which is caused by the sampling of the sequences you're analyzing. Here's a discussion of what PSD as an averaged periodogram means. What that really means is if the windows that are used are smaller size than the length of the sequence being analyzed, the PSDs are formed by averaging individual PSDs from the smaller window samples of the sequence. Like, for example, in the previous example I showed, we had a 4,096 point input sequence with windows that were 128 points in length. So what it did is it computed individual PSDs of that sequence, each PSD being 128 sequential sequences out of it, and then averaged those PSDs all together. When it's done in that form, they're called averaged periodograms. And that averaging helps, again, smooth out, in addition to the windowing, the averaging helps smooth out some of the chatter that you get around the sequences, where it's combining, doing spectral leakage and combining real signal with among adjacent sinusoids in the discrete Fourier transform. So that can be useful too. And again, this is provided primarily just so you know what an averaged periodogram really means. Again, as mentioned earlier, there's a couple other options that are available with these PSDs called detrending and overlap. Detrending is nothing more than removing trends from the sample data. And trends in that context just means things like a non-zero mean value of the signal would be a constant bias. Now you can do that two ways. You could actually pre-process the signal for which you're going to compute the PSD and compute its mean value and subtract it off yourself. But the PSDs kind of acknowledge something that is frequently done. So one of the options is you can tell it to do a constant detrend, and that just removes any mean value that it might have before it computes the PSD. You could also remove a linear bias if the data had such a phenomena on it. They also, the MATLAB and Octave PSD functions have a flag called, or string input called dflag, and it's input as a string. You can put the string none, which is the same as not providing it at all. That's the default action. It would do no detrending. You could put the string input constant, and it would remove a constant bias or a mean value. You could put the string input linear, and it would remove a linear bias. Overlap is similar to the averaging we talked about before, except that if you specify an overlap, that number of adjacent values of the input sequence will be included in the individual PSDs that are then computed and averaged. And so that overlap, it just slides down. If you envision sliding the samples down through where you're overlapping some number of them with each window. And again, that's just a technique to try to put in some averaging or other manipulation of the inputs so that you can more clearly isolate the individual signal content that's present. And finally, we'll conclude this section today with an example of a PSD. So we'll take a signal with multiple sinusoids, a bias, and a random content, and compute a PSD of it and see if we can interpret what we got. So we'll create a 10,000 point sample, real sequence of several sinusoids, and a uniform. And so here's the exact MATLAB calculation that was used to create that. So the first one is an amplitude 2 sine function at 200 hertz and 10,000 samples. The second component is a cosine, unit amplitude cosine, at a frequency of 400 hertz. Again, 10,000 samples. The third one is a unit 4 sine wave at 150 hertz squared. So this sine wave is squared at 150 hertz frequency. And then finally, we'll add to it a uniform, just random variable that's distributed uniformly between plus or minus 2.5. If you compute that signal as shown there and then plot it out, as shown in the figure to the right, you'll see time history of the data. So now the goal of a PSD analysis is to try to take such a waveform and see if you can determine what's in it. What sort of sample frequency, what sort of sinusoidal frequencies might be present. And this might be sensor data from a real piece of hardware that you're trying to characterize. And either for modeling purposes or maybe to compare it to some specification that says the energy at certain frequencies has to be within some specified ranges. So the first thing we'll do is we'll call the PSD function with this new 10,000 point real sequence, and we'll provide non-default values for the FFT size. We'll tell it we want 128 points for the FFT that's used to compute these PSDs. Sample frequency is 1,000 hertz. The window parameter, we'll just provide a positive integer input of 128. And recall what that would do in the MATLAB function was it would provide a 128 point Hanning window. It would then divide this 10,000 samples XMN into 128 point segments, compute the FFTs of each segment, average them together. We'll also provide no overlap, and you'll see in the function call below the overlap has been provided as an empty input, which means it'll use the default none. And then we'll provide the constant D-trend that will remove that mean value that we intentionally put in on that signal. So then the actual calculation that you would, our inputs that you provide to the PSD is the input sequence X, 128 for the size of the DFT, 1000 for the sample rate, sample frequency, 1000 hertz, 128 for the window, null input for the overlap, meaning let it use the default of no overlap, and then a string input of constant for the D-trend, which will remove the bias value. Now shown on the right is the output of that, where I've plotted the PSD returned in the variable PXX versus frequency. And again, note now the frequency range is in hertz, since we provided the 1000 hertz as the sample frequency to the function. And also notice now we see 4 prominent features in this PSD. We see 3 distinct frequencies, 200, 300, and 400 hertz. And we see what looks to be a kind of a constant floor value running along at a constant, this basically constant, not a function of frequency, if you will. And we'll discuss each of these on the next page. Okay, now as you'll see, we'll discuss the PSD that we showed on the previous slide. Again, over on the right is shown the output of the PSD function for this signal, 10,000 sample signal that we provided. But now you'll notice the 3 distinct frequencies are shown up, 200 hertz, 300 hertz, and 400 hertz. Now the 200 and the 400 are expected because we had actually put in sinusoids at 200 hertz. It had an amplitude of 2. We had a sinusoid at 400, which had an amplitude of 1. But we put in a sinusoid at 150, but it was squared. And so if you remember some of your trigonometric identities, that sine squared of theta is like 1/2 of 1 minus cosine 2 theta. So then that 150 hertz sinusoid that was squared shows up like 2 times 150 now in the actual, or in an equivalent representation of sine squared 150 t. So now that 150 hertz signal is now showing up at 300. And also you notice the amplitude before for that signal was 4 times sine squared. Because of the half that you get with sine squared being 1/2, 1 minus cosine 2 theta, that shows up as equivalent to an amplitude of about 2. So now it's comparable to the amplitude of the 200 hertz signal, which also was 2. And you'll notice those are both approximately 4 times the signal of the unit amplitude, the component at 400 hertz. And that's what you'd expect there, since this is signal squared amplitude is what you get out of the PSD. In other words, units squared per hertz. And also, what's the constant level that we saw that I described on the previous slide, where it looks like there's a constant line that's independent of frequency? What that is resulting from the random component of the uniform. As I said, in the sequence we created, we included a uniformly distributed random variable that occurs between plus or minus 2.5, as in addition to the distinct sinusoids that we put in. So the theoretical line for that random component should be 25, there's amplitude squared, 25 divided by the sample frequency over 2, or basically 0 to 500 hertz for the range of the real DFT, times the theoretical variance of 1/12 of a uniform signal that varies from plus or minus 1/2. You do that calculation, you should get the value of 0.417 for the mean square value, and it should be a constant over that whole frequency range of 0 to 500. And that's exactly what you see. The black line that's superimposed now on top of the blue line, which you can barely see, is that level of constant 0.00417. So what we've seen from this now is this PSD of this input waveform has correctly extracted all the elements that we put into it. It's extracted the constant part due to the uniform random variable that we added. It's extracted the individual components of 200 hertz and 400 hertz that we put in. It also correctly extracted the 150 hertz sine squared term that was there. So this example shows gives you a real good feel for how you can use PSDs to take a signal that looks pretty noisy or pretty ratty and figure out what content it really has, spectral content that is. And again, just one final word, I'll expand it a little bit more to show the area around that constant line, just to show how well it does fit through the theoretical line. The blue line, again, is the theoretical value, and the red line is the actual PSD. And also, a thing to point out is you can calculate the mean value by just summing up the PSD values and multiplying them by the frequency per data point, if you will, and that's what the calculation shown here towards the bottom is, where I've just actually summed up PXX and multiplied it by the last frequency divided by the length of the frequency array, and that comes out to be an RMS value of 2.515. If you take the 10,000 point waveform itself as provided and just compute the standard deviation, the mean value, and the RMS value, you can see then that the 2.515 that we get out of the PSD function matches the actual RMS value very closely. It's not exact because one of the reasons is we removed the mean from the signal before we computed the PSD, so if there had been a significant mean compared to the RMS value, then we would have gotten what looked like a farther off from the real answer, but it's expected since we had removed the mean. One final example, or comment I want to make here, is what would happen if we had not provided the detrend option to the PSD to remove that mean. So without it, the mean value that we built into this test function actually is included in the PSD. And you recall what that would do, if you remember from part 1 of this presentation and other comments I made in this presentation, the mean value would show up as a zero frequency component in the PSD or in the discrete Fourier transforms. And so what you see now in this plot, again, which is expanded out, but you'll notice now down around zero frequency, you see a spike in the red line from the PSD, which wasn't there previously. So what it's done is taking that mean value that has not been removed in this example and applied it to zero frequency. So typically what you'll see if you haven't pre-processed some sensor signal or some other signal that you're evaluating and you see a DC component, in other words a zero frequency component, that indicates that the signal you're evaluating has a non-zero mean value. So just be on the lookout for a spike in the PSD at zero frequency, because that's what it means. So this concludes part 2 of this 4-part series for digital signal processing. In this part 2, Power Spectral Density Basics, we covered the following. Primarily, the use of power spectral density techniques to estimate the spectral characteristics of waveforms. We showed a couple of examples, and particularly an example where we built a waveform of several known sinusoids and then used PSDs to demonstrate how you can evaluate those and extract the frequency content. In part 3 of this 4-part series, which is entitled Implementing Discrete Filters, we'll cover the following. We'll also discuss how to convert from continuous Laplace domain filters to discrete Z-domain filters using what's referred to as Tustin's rule or the bilinear transformation. And that's a technique that then we can use just to replace the S operator in Laplace transforms with a Z operator in Z-domain filters. We'll also show how to implement recursive filters to affect discrete filtering. In part 2 of this series, which is entitled Typical GNC Applications, we will cover the following. The concept of normalized frequency, some of which was touched today as well as in part 1. We'll also talk about methods to verify transfer function magnitude and phase for a discrete filter if you've been provided discrete filter coefficients and you want to double check that you're getting what you think you're getting. We'll also show an example for how to use the discrete filter to implement a notched low-pass filter. And so we'll build a notched low-pass filter, and we'll also build an input waveform that has frequency content at the notch and at higher frequencies, and we'll show that the filtering does remove those characteristics that we would like to remove from the waveform before you might use it for other processing in a flight control system. I hope you found this presentation to be useful and informative, and I invite you to continue with parts 3 and 4 of this discussion. Thank you.